Right. Hello, everybody, and welcome to June's Global Health Compound Design webinar. And today I'm really pleased to introduce Vincent and Antoine from the Swiss Institute of Bioinformatics, which is the largest national bioinformatics network in Europe. And they have created a huge number of valuable tools and resources that are all freely available via their XBASI portal. The Institute focuses on creating, maintaining, and disseminating a large portfolio of top quality core bioinformatics services and resources that includes databases, software, and competence centers. It also includes a range of drug design tools which cover both molecular docking through to virtual screening tools and target prediction of small molecules. And in January, they launched their SwissADME service, which is a free web tool to evaluate pharmacokinetics, drug likeness, and medicinal chemistry friendliness of small molecules. And I'm very happy to invite them to tell you about this resource today. You're all muted at the moment, but if you'd like to ask a question during the presentation, then please just type it in the question box, which is at the bottom half of the control panel. And then we can put them to Vincent and Antoine at the end. There's going to be a short presentation first, and then they're going to do a live demo to show you exactly how the tool works. Okay, over to you, Antoine.
Yes, thank you very much. Yeah, my name is Antoine Daina, so I'm a member of the molecular modeling group of the Swiss Institute of Bioinformatics, who are located in Lausanne, Switzerland. And Vincent Zoete, who will introduce you some of our other tools, is the group leader of the molecular modeling group. So this is the proposed agenda of the seminar. So there will be something like 30 minutes presentation of the back end of SwissADME. Then Vincent will introduce you very rapidly the other tools we have for computer-assisted drug design. There will be a live demo of SwissADME, of the website itself. And of course, this includes totally open discussion. If you have questions, if you have remarks, we are very pleased to discuss and have your views on our tools. So no big introduction on ADME, just these intro slides. So the causes of failure of oral drug at clinical phase, more precisely phase 2 and 3. Till the 80s, maybe the traditional way of doing medicinal chemistry is made for making very potent compound, and then later on taking care of pharmacokinetics. And you had the most of the failures are because of pharmacokinetics of ADME in phase 2 and 3. And we made a lot of progress in the sense that nowadays there is a clear reduction of the proportion of PK and ADME causes of failure of drugs. And one of the main reasons is that in the drug design process, we estimate earlier and earlier absorption, distribution, metabolism, excretion, even at early discovery phase. And this trend is going on actually, in the sense that we try to be even earlier in the process where the number of molecular structure to deal with is very large, but the availability of the compounds is really scarce. So this has pushed the development of computer models to predict ADME from the chemical structures. So to estimate ADME behavior and pharmacokinetics related parameters for drug discovery or drug design, a computational model should be, of course, robust, because you need a reliable prediction. It has to be fast, because you need a quick answer, because maybe the number of structure is really big, or because you want to enter a cyclic iterative way of optimizing the compounds. And very importantly, it has to be descriptive enough to be translated in chemical terms. So you are able to interpret the prediction in terms of chemical structures So you can select molecular structure or modify the molecular structure to target specific properties. We developed the SwissADME tool, which is a web tool to make the community able to access to multiple models for predicting and calculating physicochemical parameters, because these parameters are directly related to ADME. Individual pharmacokinetic behavior, also with graphical output, drug likeness, and other parameters that we gather in the medicinal chemistry friendliness section. In SwissADME, a model can be a novel approach out of our basic research, like the ILOG-P or the boiled egg I show you later. An implementation of an existing published model directly or with some adaptation, or the building of a model based on existing data but with different descriptor and or statistical machinery. So the descriptor has to be simple, has to be not so many, and absolutely open, so freely computable for anyone. The statistics has to involve a very simple machinery. So if we do regression, normally we use linear regression. When we do classification, normally it's support vector machine. We published the clean, cured data sets, so it's totally disclosed. In terms of scripting, the languages are really common. All these to have a full control, flexibility, robustness, and also very important to be translated into chemical structure through molecular design. So the SwissADME input page, so it's totally free from non-profit organization. We made no guarantee about confidentiality, so the molecules are kept on our server for statistical purposes. It's totally without logging. There is no CAPTCHA. So when you type SwissADME.ch, you enter directly the input page, like on this screenshot here. And this input page was developed as much as possible in a user-friendly fashion, because our philosophy is that our tools has to be useful for specialists, but also useful for non-experts in the chemoinformatics or computational chemistry field. So the real launch of this website was last year, but the website was published in 2017, so this year. We already got an important number of users and jobs and compounds. As you can see, every month, in average, we have 5,500 jobs, which represent between 20 and 25,000 compounds calculated. So some of the advantages of this interface is that you have different ways of inputting molecules in. We'll see in the demo. You can enter a series of molecules, not only one, but you have a series of molecules that can be opened in a list. And the result is returned is in about 3 to 10 seconds for a drug-like molecules. This is the output. I don't want to go too much in detail because there will be a demo of the website. I will give you some information about how we built some of the models in. You'll see that there is a panel, so one panel per molecule with all the predictions, all the data, all the models, but we also have a graphical model at the end of the calculation of the list of molecules that is more intuitive and more easy to interpret for some ADME behaviors. So I will focus on lipophilicity. I will focus on some classification model for pharmacokinetics, and maybe on the medicinal chemistry part if we have time. So the prediction of lipophilicity, one of our idea is, when possible, is to implement multiple models for the same property, either to let the user select the most suitable model for his specific question. Here for lipophilicity, all methods have strong points and weaknesses, but if you are experienced, or if you make some tests, you can maybe select the best method for your specific chemistry. Or to have a consensus view. So here the consensus is simply an average of the 5 methods, of the 5 predictors, which can be classified in 3 different categories. So the fragmental way of predicting lipophilicity, the topological methods, and the physics-based methods. So very briefly, the fragmental methods is really at the origin of the computation of log P. So you have fragmental systems like this one, which is obtained by training. So by training, for instance, Wildman and Crippen publish this dictionary linking atom with contribution to the lipophilicity. So this is really a screenshot of our code. So because we re-implemented this fragmental system. And so the principle of estimation is you input a molecule that is cut into fragments, and every fragment is retrieved in this dictionary, and every atom's got a contribution plus or minus. Here on the paracetamol, for instance, you have positive contribution of the carbons, negative contributions of the polar atoms here. And for the W log P, which is this specific method, there is no corrective factor. So it's only a sum of the fragmental contribution. You can have corrective factors with other method, like if it detects the possibility of internal edge bounds, it lower a little bit the prediction, and so on and so forth. It's a very good method. It's very quick, but it has some drawbacks. So this additive nature make that there is very often an overestimation for big molecules. The fragmental system cannot cover the entire chemical space. So if you don't have a fragment inside corresponding to your molecule, you have a dummy value, and you have a moderate dependent to training. So you can have overfitting, meaning that if you are trying to predict a molecule that is very close to the molecule that has been made to generate this dictionary, the prediction will be reliable. But if you get out of the chemical space of the molecules that have been used for training, you have a less reliable prediction. The other method are topological. So the principle is QSPR, so quantitative structure property relationship. The description of the molecule is according to a descriptor related to topology, and you use the statistical model to make a prediction. One of the best known example is the M log P from Moriguchi, which is a very complicated equation, but it's still a linear equation with 13 terms, among which very ambiguous one. As you can see here, this is a copy-paste of the publication. Interestingly, Lipinski published a revised rule of 5 with M log P less than 4.15 instead of C log P5, and because you can use M log P, which is a totally open and free way of predicting log P, whereas for C log P you need a commercial license. So also some drawbacks: high dependence to training, so high risk of overfitting, and these parameters very complicated, sometimes lack some physical and chemical meaning, which limit the chemical interpretability and limit the use for drug design. Also, because some of these parameters are very ambiguous, you have a low reproducibility of diverse implementation. So we implemented our M log P, and it does not give exactly the same prediction compared to the 20 different implementation of M log P. This is something we have to live with. So we also have our own machinery to predict log P, which is quite different actually. It's the iLog P, and it's purely physics-based in the sense that you try to model what happened in the ampulla when you make the log P measurement. So it's really calculating the solvation-free energy in octanol and the solvation-free energy in water. So the Gibbs energy of solvation is composed of an electronic part, which is calculated with the generalized Born method, and a non-polar part, which is estimated by the solvent accessible surface area. And we generate some parameters out of this physics-based calculation, and we do multilinear regression to get to this equation here, linear equation here. And we were very happy to see that the slope is almost 1, the origin is almost 0, and this factor here makes total physical sense. You can go to a level of analysis that permit design, so permit to know exactly what part of the molecule make it more hydrophobic, hydrophilic. We have less overfitting, and it's an original method. So for consensus, it's good to have a prediction of log P that is pretty different. Of course, you have some drawbacks. Of course, we need force field and GB parameters. We know some function are misestimated, and the calculation is a bit longer because we really generate and optimize the molecule in the solvents. But it's still 1 to 2 seconds per molecule, which is manageable, right? The second topic I want to introduce is a classification model for pharmacokinetics related behaviors. We have classification models, 2 kinds. One is related to the boiled egg, and the other one are support vector machines. So all are to predict binary classifications, so high or low, for instance, for gastrointestinal absorption, yes or no, really this kind of classification method. So if we concentrate first on our method, which is called the boiled egg, I don't know if some of you is familiar with this depiction here, which is the egg neck. So Mr. Eggen was able to point out a zone in this referential of A log P98 and polar surface area of a compound that are known to be well absorbed. So it's really a great practical utility. You have a lot of citations. I used it a lot when I was in the industry. It's also implemented in some commercial packages. But it has a few drawbacks. It's really hard to reproduce because these are closed source descriptors. So A log P98, you need a license to calculate, and the PSA is generating really by generating the 3D, getting the surface, and it's very difficult to reproduce this part. Also, the data set is partly undisclosed, so it's not possible for us who want to make something open and accessible to anyone to implement this model. Another drawback is that it's purely descriptive, so it's purely the spread of the compound that are known to be well absorbed. Even though it is used in common practice for a prediction. So we try to patch this. We get a data set from the literature. We made some standardization, and we use totally open and ambiguous descriptors. So the W log P, the log P I showed you just before, that is published, all the fragments are published. And the TPSA, which is also a fragmental system to estimate the topological surface area, so totally reproducible. And we generate this heat map, which is, so in this referential, W log P and TPSA, which represent the region of the space If it's red, pink, and white, these are the region of the space that are most populated with well-absorbed molecules, whereas blue and very dark blue are the regions of the space with experimentally determined low-absorbed molecule. So there is a clear signal, as you can see here, and it can be an ellipse, right? So we say, let's try to build our predictive model, so finding the best classifying ellipse. So we made a lot of work in curating data from the literature, so lots of cleansing, but also we curated for passive absorption. So we wanted to make a model only for passive absorption through the gut wall and not excluding the compounds that are actively transported by a transporter. So we get to 660 molecules, mostly well absorbed and some poorly absorbed molecules. And we defined the ellipse this way. So we started from the geometric definition, so the coordinates of the two foci and the two distances, here the two diameters, to define the trace of the ellipse. We optimize with a Monte Carlo optimization. So we generate the first ellipse with the first parameters, and we evaluate for classification. Then we perform the random change. So a new ellipse is generated. And again, we evaluate for classification. We use a metropolis criterion to keep or reject the new ellipses. This is one run. And we repeated this loop. So this run 100,000 times. And we repeated these 100,000 times, 100,000 times on different starting points. So we had 10 million ellipses to evaluate for classification. We used the Matthew correlation coefficient to assess classification, so true positive, true negative, false positive, false negatives. It ranges from -1 to +1 for perfect prediction and near 0 for random classification. We observed empirically that at the beginning of the MC optimization, we got an exaggerated growth of the size of the ellipse. So we had to put this little constraint on the surface, and we got a score. So all the optimization is to optimize this score here. And among the 10 million ellipses, we get this one, which is the best classifying one. So the one that put the blue point, experimentally well-absorbed molecule, inside the ellipse, and the green square outside of the ellipse, which corresponds to an MCC of 0.7, which is here accuracy of 93%. This is in accordance with the usual guidelines reported for good absorption. And this is not so far from the egg and egg. And remember that these axes are not the same, and the data set is very different. So we were very pleased to generate something that actually makes sense. We performed tenfold cross-validation, so really to assess the internal robustness of the procedure of the model. So in dashed line, this is the actual model, and we split the data set into 10 different pairs of training set and validation set. And these 10 new cross-validation models are the color ellipse, and as you can see, even though you extract 10% of the observation, you can see that it doesn't move so much. So the variation are really low. We have statistics, of course, but it shows, this picture shows the internal robustness of the model, even if it's very intuitive and simple, only 2 parameters. So we say, why not pushing the thing to another very important ADME-related physiological barrier? And we said, yes, let's try for the BBB. So the most tedious part was to cure for passive permeation through the brain. So we got 260 permeant and non-permeant molecule from the literature. We perform exactly the same heat map, and the signal is absolutely clear, and the space populated with permanent molecule is narrower, which makes sense because the BBB is much more difficult to pass through passively than the gut wall, right? So we say, okay, let's perform exactly the same method of optimization in the same descriptors, 10 million ellipses, and this is the best one. So the one that classifies best the BBB permanent from the BBB non-permanent molecule. These are the numbers, again, consistent with the common guidelines, and internal robustness that is perfectly assessed by tenfold cross-validation. Right? So we have 2 models in the same referential, very intuitive, we are allowed to merge the two models. So for gastrointestinal absorption and CNS brain permeation. So we get very creative in choosing the colors here. As you can see, the yolk, so the yellow zone is for the region for molecules that are well accessing the brain. The white is for molecules that are passively absorbed by the gut, and outside means that there is no absorption. Also, a good acronym and a nice picture on the journal we published this paper. We made a few exercises, so we were able to track back retrospectively some very restrictive medchem papers, like for instance, the optimization of ponatinib from an initial hit. They are very descriptive in this paper to show how they try to focus on PD and then on PK to get back. So I don't want to go too much into details because there will be the demo session then. Another exercise is that we mapped the 46 new chemical entities accepted by the FDA in 2014 and 2015. We color these molecules according to usage labels. So blue dots is for oral administration, and the crosses, the green crosses, as for other routes only. And we had 83% consistency. But interestingly, as you can see, there are some outliers. So you have false negatives, like this daclatasvir here, which is an anti-hepatitis C compound that is, sorry, very polar, very big. So all the properties not to be well absorbed, but actually it's well absorbed. And when you look in the files, the reason for this is that it's actively transported by OCT1, which is a well-known transporter. So this is outside of the validity domain of the model, right? Here, the boiled egg is only for passive absorption. Here, it's actively transported. The contrary is also true. This is an anti-asthmatic drug that the molecule has all the property to be extremely well absorbed, but actually it's not. The fraction absorbed is 10 to 20%. Why? Because it's actively effluxed back to the lumen through this very well-known PGP active efflux pump. So it's a protein that effluated from the brain, but also back to the gut lumen molecules. So we have to take this into account as well if we want a better view of absorption and distribution in the CNS. So this is a transition to the other classification model we have in SwissADME. We have classification models for cytochrome inhibitors, but importantly, in our context, a PGP substrate classification model by SVM. So I don't know who knows SVM. So very briefly, it's a machine learning pattern recognition algorithm, which is mainly used for binary classification. So the objects are divided in two groups and divided by the widest gap as possible. And the prediction, of course, is to see how the new object is mapped onto one of these two groups. This is a very simplified view. So two groups plus and minus, let's say PGP substrates, PGP non-substrate. The idea is to construct a hyperplan. So here it's a linear SVM with two descriptors. So it's an exercise only. So here it's a line. So you try to find the best line with the widest margin here to separate the two groups, right? But there are a few tricks. So some tricks is to control the permissivity of the soft margin here, because sometimes it's good to have one molecule switching to the other group. It it increased the predictive capability of your model actually, and this is controlled by a parameter C. And the other trick is that normally you don't use linear axis, but you transform the space with the Gaussian function to spread all the parameters that can be extremely numerous, maybe 15, 20, 50 different axes of your matrix. And to spread this, you need to use a kernel function, and the Gaussian function is controlled by this parameter gamma. So to build our PGP substrate model, so telling you if the molecule has the property to be more likely to be PGP substrate or not, we cure a big test set here and training set, and we calculated all the descriptors available in SwissADME, also the ones that are not appearing in the web page. They have to be descriptive enough, and they have to be orthogonal. So a lot of tests and a lot of optimization. So we use an exhaustive grid search to find the best combination among the descriptors and among the two parameters of the SVM itself, so the margin permissivity and the transformation of the axis. And we get the best combination of 15 descriptors. Finally, with that, we get a classification accuracy at 72% by tenfold cross-validation and almost 90% on the external test set. So it's not 100%, it's a classification method, it's a quick one. We describe the molecule only with molecular and physicochemical parameters. So we will never reach 100% external and with cross-validation. So we have to keep in mind that there is, the performance are good, but it's not 100%. So this is the boil deck I will show you in a few minutes, as implemented in the SwissADME website. So it's a bit an enhanced version, because you have, of course, the prediction of the passive absorption and passive access through the brain, if the point is inside the white or the yolk, but also the color of the dot corresponds to being predicted as a PGP substrate or not. For instance, here, palonosetron is accessing the brain passively and stays there, whereas sunitinib, this anti-cancer drug, is accessing the brain, but effluxed being a substrate of the PGP. Yeah, I take 1 minute only to tell you that in the medicinal chemistry part, we have implemented some alert of problematic fragments. So toxic fragments, reactive fragments, aggregator fragments, dye. Medicinal chemists know that, and it's a very simple machinery to try to retrieve the fragment in the molecules and give some alert on that. Paints also, and specific frequent ethers, of course, it's very important. And we have a synthetic accessibility score we can talk about if you are interested later. So this very clever statistician get this statement: all models are wrong, but some are useful. And in exactly the purpose of SwissADME, we are not trying to predict the absolute truth. We are not trying to predict reality. We are using statistical model as predictive as possible, but ranging from 70 to 90% capacity, trying to extend as much to do extrapolation. But there is always this margin of having, of course, wrong prediction. The idea is to get as much as possible an idea of how to triage the molecule, how to filter, how to prioritize, and generating some ideas for design regarding pharmacokinetics parameter. I will let the presentation to Vincent that will give you a brief overview of the other modules that can maybe help the discussion later.
So thank you, Antoine, and good afternoon, everyone. So yeah, I just wanted to take a couple of minutes to remind you that in fact SwissADME that Antoine is introducing today is part of a larger initiative coming from the Swiss Institute of Bioinformatics. And as you know, and as was introduced by Caroline, we are actually working for the Swiss Institute of Bioinformatics to develop this project. So the project is called Swiss Drug Design. You won't find any website called Swiss Drug Design because, in fact, it is the name of a collection of tools that are findable online, like SwissADME. And the purpose of the project is actually to try to address the questions along the drug design pipeline using different types of approaches that we can roughly characterize as structure-based and ligand-based. So structure-based approaches are everything that you can do when you know the three-dimensional structure of the targeted protein. And basically, the cornerstone of structure-based approaches is docking, and we have a tool for docking, which is called SwissDock. The second part of approaches that we can define is ligand-based approaches. So that's everything you can do when actually maybe you don't know the structure of the targeted protein, but you have access to a list of molecules that are already experimentally active that can come from the competition, from nature, or from your own library. And you can use machine learning technologies, for instance, to extract information from these ligands and try to use that in order to make even better molecules in the next round. So as you can see, we have made different tools that are already online. So those correspond to the blue ones on the slides. If you just add a .ch after the name of the tool, actually you will end up in front of the tool online. The green one corresponds to future tools on which we are currently working. So I will just make a one-slide description of those different tools very rapidly. So the first one is a structure-based tool, actually, that is also the first one from an historical point of view. So the idea is that we developed a docking software, and we wanted to provide a free access to this tool and a simplified one so that we can actually provide this type of technology also to non-specialists in molecular modeling. So the idea is that if you know just the name of the protein, you can provide the name online, and we will fetch the three-dimensional structure of the corresponding protein for you, and we will automatically optimize it for you for the docking. You can do the same for the ligand. Once this is done, we perform the docking directly on our machines here in Switzerland, in the Swiss Institute of Bioinformatics, so that you don't need to provide the computational power. And when the docking is finished, after some minutes, 2 hours, then we provide you with the results directly in your web browser in 3 dimensions, so that you can analyze the results without, again, the need for you to install any software on your machine. So this is typically the type of approach that we are using. And as I told you, actually, all those tools are login free and also free for usage in academia and for non-for-profit organizations. And other tools that were developed for structure-based approaches are actually more technical and more dedicated to people working in molecular modeling. So I will not spend a lot of time on them, but basically they allow the people to get everything they need to make calculations using small molecules and peptides based on non-natural yet commercially available amino acids. Then we have a collection of ligand-based approaches. The first one is SwissBioisoster. So this is something which could be quite useful for lead optimization, actually. So the idea of SwissBioisoster is to be a database of 4.5 million molecular replacements that were all tested experimentally and published in medicinal chemistry literature. So we collected automatically all those data, so that now if you'd like, for instance, to replace a pyridine fragment, like on the top of this slide here, we can provide you with a list of possible replacements that were all tested experimentally. And for all those, each of these replacement, actually, we can provide you with statistics regarding the efficiency of the replacement on the activity against a given target. We can provide you with this kind of data for each target. We can analyze it. We can provide you also with the effect on the physicochemical properties of the small molecule. We can provide you with a list of every single molecule where the replacement was done, along with the corresponding references in the medicinal chemistry literature. So we hope that actually this could be very useful for your usage. Another tool that we develop is called SwissTargetPrediction. So you can guess that actually the purpose of this tool is to predict possible targets for a small molecule. So as you know, a bioactive molecule has its activity explained not only by the primary target for which it was developed, but also by its affinity for secondary and unexpected targets. And it can be very useful to identify those targets in order to determine the possible toxicity of the small molecule, but also to maybe figure out whether there could be a possible drug repurposing for some compounds. So the idea of SwissTargetPrediction is that we have collected a library of 300,000 molecules for which we know exactly experimentally the targets of those compounds, so that if you provide us with another compound which is bioactive, then we can compare systematically your molecule to find out which one in our large library is similar to this one, so that we can actually use our statistical analysis to also calculate the probability of your molecule to be active against different targets in human, but also in some other species. We have also developed another tool using the same type of approaches to perform virtual screening this time. So if you already have in your hand a molecule which is active against a given target of interest, and you would like to find molecules that are similar in terms of chemical structures or in terms of three-dimensional shapes, then you can just draw your molecule in this tool, select a library of bioactive molecules, commercially available ones, or even molecules that you can synthesize by click chemistry from sigma-aldrich compounds, and after a few seconds you will be provided by your list of molecules which are actually similar and that you could potentially buy or get very easily, and you can analyze then these molecules because they are ranked according to their similarity. Last but not least, we have developed the SwissADME web tool that actually Antoine is right now presenting to you. And before I will give back the hand to Antoine, I will just underline 2 points. The first one is that since we are developing all those tools, actually, we can also develop the interoperability between those tools, which means that in the future, you will be able to use the output of one tool as an input of another tool automatically by just clicking on an icon. For instance, if you find by virtual screening a couple of molecules which are interesting potentially for you, you could get the ADME properties by just clicking on the corresponding icons or molecules. Also, the second point is that we are planning to make another webinar during this autumn, and for the moment we plan to do it around the SwissDock docking tool, which is already online. However, maybe you could consider that actually other tools could be also very useful, like SwissBioisoster, Target Prediction, or SwissSimilarity for the virtual screening. So in case you would prefer us to change the topic of the second webinar for one of these ligand-based tools, please just contact us and we will be happy to change the topic of it. So thank you very much for your attention, and I give back the hand to Antoine.
Okay, thank you very much. So now, according to the schedule, there is a live demo of SwissADME. I don't want if you have some very important question before. Caroline, can you tell me if I go on?
We don't have any desperate questions at the moment, so please go ahead.
Okay, great. So our web tools, SwissADME in particular, is you got the best experience with Firefox, Chrome, and eventually Safari on Mac. What we cannot guarantee is to have the best experience with the Microsoft browser, because they are a bit different. So this is Chrome. So to get to SwissADME, very simple. You type swissadme.ch in your browser, and no login, no captcha, nothing. You get directly on the on the website, on the input page. So you got always this black bar here to navigate through our different tools. You can see like SwissBioisoster, SwissTargetPrediction, SwissSimilarity. Here you have the gray toolbar, which is, you have a disclaimer, you have some help page that tells you how to enter a molecule and so on and so forth, what we will see, and frequently asked questions, which answer the most frequently asked questions we got, right? If you want to get more information, we are totally transparent and giving all the details in the publications you have here. For instance, there is this scientific report about the website, but also about some of our other models here. Okay, so the input, you have the a molecular sketcher, right, to design molecules. You can see that when it's empty, this arrow here is gray. When it's when you have something inside, then you have this, which is active. You can draw a molecule, but you can also import a molecule. So here you have the import button. And if you have a very well-known molecules, like a drug, like Primaquine, for instance, you can import directly, get the molecule, and then clicking here, adding the molecule to a list. And this list is the real input entry of SwissADME. You can enter one molecule, but you can also enter multiple molecules. One molecule per line. One molecule means a smiles, then a space, and then a name. So here we are, Primaquine. And then the next one. The next one can be a file on your computer. So you open a file, and somewhere of my own computer, I have this SDF file here. I can open. Here is the structure of atavaquone. This is the molecule, space, a name. Here, you can have a blank line or not, makes no difference. And when this list is filled, you have the run button that is active. So you can run, and then you have this little rolling thing for each molecules, but you don't have to wait the whole list to be calculated to get the first panel here. So here the first panel is Primaquine. You can see the structure, you can see a normalized canonical smiles. You have the different physicochemical properties, the lipophilicity, some model of water solubility, the classification models, drug likeness filter, so rule of 5, but not only, and the paints, the problematic fragment, leak likeness, and synthetic accessibility.
Antoine, can you make the screen a little bit bigger?
Bigger. Is this better?
It's a little bit better. Yeah, that's better. Much better.
Okay.
Yeah. Okay.
Much better. Okay. So I hope you've seen.
Yeah.
So you can see Primaquine. Look at this radar here. So we call it the bioavailability radar. So it's according to 6 properties, so one on each axis, so lipophilicity, size, polarity, solubility, saturation, and flexibility. And we define a zone. If you let the arrow, so the cursor on, you have an explanation of the different axes here, the different parameters. But the thing is that we define a pink zone here, which is optimal, the optimal properties and for a compound to be bioavailable. So the radar of the molecule has to be fully in this pink zone to be considered, estimated at first as bioavailable compounds. If it's outside of the radar, so the specific property is suboptimal. So here you have this Primaquine, which is absolutely drug-like. You can see also the drug likeness filter. You can see also gastrointestinal absorption, that is no alert, everything's okay. Atavaquone is a bit different. So it's still a drug-like compound, but we are really at the limit. So lipophilicity seems to be suboptimal. It's too much saturated or at the limit of saturation, at the limit of solubility. So you have a compound that is still a bioavailable compound, let's say a drug-like compound, but surely not optimal gastrointestinal absorption, not optimal PK, which is actually the same. Atavaquone is absorbed not so well and very dependent on your diet. You can see that here on this molecule, there is a pain alert. So it's able to detect a quinone here, as you can see, and more benzoquinone. Not said that it's automatically a pains compound or a promiscuous compound, but this is an alert when you have to triage, when you have to prioritize. Maybe having a quinone is not the best thing to try. Here, maybe because of the substituent, it's okay, but the alert is in, right? Okay, let's try another example to show you all the things. So I went on the open source malaria wiki. and get interested in this series 3, so the aminothienopyridine series. I took here, there is a initial hit here, which is this compound. So let's try to put it in SwissADME, so we can clear the list. There is the smile given, so I can simply copy and paste it in the list. I can give a name. I will give the code of it. So copy, paste. Down under, there is just below, there is another interesting compound here. I put the smiles, I put the space, I put the name. If you omit the name, the compound is called molecule and the number of the line. So we can run it.
You just missed the N from the beginning of that second line on the smiles.
Sorry?
You just missed the N of the first.
Sorry.
Yeah, okay.
Of the first one?
No, second one.
Second one. Is it okay now?
On the smile string, it should start with a nitrogen.
I think it's okay now.
You think it's okay? Okay.
So, yeah, I think so. Maybe it was out of the screen.
Possibly.
Yeah. I extended the size of so much that maybe it was outside, but you can extend the thing here. Sorry.
Okay.
So okay, one panel per molecule. The first one seems to be really not drug-like. So you have violation of some drug-like filter, mainly linked to TPSA, so the polar surface area. So the molecule is too polar to be well absorbed. This is shown in the boiled egg. So if you click on this red button here, you have an accordion opening the boiled egg. You can hide it, of course, but you can open it this way. So as I show you, so you can show the molecules names here, and this is the first molecule. So this first hit of this series, right? If you let the cursor on, you see the structure, right? So it's a molecule that do not have the properties to be well absorbed, and mainly it's because of TPSA. It's too polar, so it's outside of the egg. The other one, so this one, maybe they made the normal trick of doing bioisosteric design, so replacing the sulfonamide by a urea, and then further decoration. You can see that it's inside the egg, but it's also predicted as a PGP substrate, so potentially pumped out back to the lumen. So the absorption is not so sure for this one. So the passive absorption is high, but it's also a substrate, so it's pumped out, right? Plus, you have problem with saturation. So what I want to show is that you can try to optimize directly some properties. So let's say we take the second one, we copy the smiles and paste it into the molecular sketcher, and you can modify your molecule. Actually, you were perfectly right in the sense that there should be a nitrogen here. Sorry, Caroline, I was looking for another nitrogen. So this is the real molecule we are talking about, right? And we say we will modify it. So let's modify. We say, yeah, but maybe I will reduce polarity. So I will go replace heteronitrogens by carbons. I paste this molecule on the new line, call it design 1. I can go back very easily, and then I will change something else. Maybe it's useless to have this H bond donor, so I will make this kind of cyclic urea, and this will be design 2, right? And I will try to change something else. I would say, okay, I want to put a polar atom here. I will change this nitrogen here and put an oxygen here, and this will be the design 3. And then you can rerun the calculation. So the two first will be calculated again. Of course, you can skip this part, but here for clarity, I let everything calculated. So the designs. So you can see that design 1 again is highly absorbed. It's still a PGP substrate, so the changes were useless. Plus, there is an alert here. Of course, this is an aniline. This is an aniline here, and this means that we should see the thing. It's not the case. So the aniline here is potentially problematic because it gets toxified by metabolism. Even though it's only an alert, it's not said because maybe these fused thiophene render the thing not so toxic, but actually it's an alert. Design 2, also useless in the sense that it's highly absorbed, but still a PGP substrate. Design 3, great, we escaped from PGP substrate, so it's still highly absorbed, but not predicted to be pumped out. This can be seen again in the boiled egg. So this compound here is design 3, right? So let's try to go on because this is far to be a lead, right? We want to transform a heat to a lead, but still it's very saturated and it's too big and too hydrophobic to be a lead. So let's try further transformation. So we can copy and paste. And we want to go very drastic, making kind of the normal trick, means replacing a urea by an amide. And we say, no, we don't need this H bond donor. So this will be design 4. And we say, okay, I have to reduce the saturation. So I will go even more drastic and I will skip this aromatic linker and get to something, get to a cyclopropyl, and this will be design 5. So we ran the calculation. Okay, I could have skipped the first, but it's to show you the speed of the method, which is normally for this kind of molecule less than 5 seconds. Of course, if many people are calculating at the same time, it will increase a bit the computation time, but never normally exceeding 5 to 10 seconds. So design 4, great, high absorption, no PGP substrate. We reduce a bit the saturation, but still it's suboptimal and it's big and it's hydrophobic, so no chance to be a lead. If we go to this cyclopropyl linker here, saturation is okay, so the radar of the molecule is fully inside what we consider as the optimized properties for bioavailability, plus the lead likeness is okay, means this compound is in between 250 and 350 milligram per mole, less than 3.5 x log p, and not so flexible. As Vincent told you, you can, one thing, you can export, let's say you are happy with these results. It's a very simple exercise as the story is not finished, but you can export the data with the CSV in a CSV file, and you can open it, for instance, in Excel, as you can see here, or in whatever spreadsheet or even text file. You can see that all what is in the panel is here. So you can see that the design 5, which is here, is a lead-like compound, as you can see here, and all the parameters, all the calculations are in. If you say, okay, I'm very happy with this design 5, but I need to know if I can get this compound or a very similar compound. And as Vincent told you, you can interoperate with our other tool. So I don't know if I have 1 minute more, Caroline, to show you
yes,
the rest, or
fine,
should we?
Fine by me.
It's okay?
Yes.
Okay, good. So just to show you the interoperability. So this is the, let's say, best design. We click on this twin icon, and then you access automatically SwissSimilarity. The page is very similar. All our tools have the same look and feel, more or less. And you can see the compound here, right? It's a virtual screening method, so I will not go into the details, but we can screen, for instance, the zinc database, so the lead-like, because we know that this compound is lead-like and we are looking for a lead, right? So we can screen this database for similar compound according to FP2 fingerprints, so means compound that are chemically very similar to this one. So it should be very quick because FP2 is very efficient in assessing similarity. And as you can see, there is no similar compound, right? Nothing as is actually similar to this in the zinc database according to this definition. So let's try to, it was for the fragment-like, sorry. Let's try to try another method. It means not compare in terms of chemistry, but compare in terms of 3D. So how the molecule is in 3D, what is the shape, what is the repartition of the charge, the repartition of lipophilicity, for instance, via the electroshape method, which is a non-superpositional 3D method. So we can submit and we look in the zinc again. So here really, it's longer because we have to generate 20 conformation of this compound and compare these 20 conformation to 20 conformation of all the zinc lead-like compounds. So it should take less than 1 minute, but I already calculated this to be quicker. So it's really, we have screened the zinc link-like with our compounds with the electroshape, which is a 3D method. So in 30 seconds, you got these results. So these are the compounds that are similar in 3D in the lead-like subset of zinc. And this is the Manhattan score. So in fact, the molecules, the conformations are mined into vectors, and all the vectors are compared in terms of Manhattan distance. And this is the score. So 0.93 is a very good score. This means that in 3D, our design is very similar to this molecule and to this molecule, and so on and so forth. So if we look at the first one, our tools also interpolate with the external resources. So if you click on the zinc link here, you access normally the panel of the compound. And you can see here the compound that you have a few description, you have the name, so it's really the zinc 12 database, and you have the data about buying this compound, right? So you can buy this compound and test if it makes sense in your test. So this was for the first one. The second one has almost the same score, so let's look at it. So the second one has the great advantage of being purchasable in many vendors. So potentially it's more accessible. So if you have only to make a proof of concept, maybe it's better to buy this one. And of course, you can go back to SwissADME because you made a lot of smart calculation with SwissADME. So let's do it again. So if you click here, you submit this compound to SwissADME, to the first one, which is called molecule 1 because there is no name. If you go back to SwissSimilarity and to zinc, you can, for instance, copy the chemical name, put it in SwissADME, copy here, and you have the compound here. You add it in the list. You call it molecule 2, and you run. And as you can see, the first one is interesting because it's highly absorbed and non-PGP substrate. Unfortunately, the second one with this little difference of here, very small difference, it's predicted as highly absorbed, but is a PGP substrate. So unfortunately, this one that was very easy to purchase is not fulfilling our needs, whereas this one is fulfilling our needs. And it shows how you can maybe go back to screen other databases, get more information, then calculate the properties, and doing this kind of iterative cycles of optimization according to multiple properties. With that, I'm done. I've shown you very briefly some of the capacities. Of course, there are more, but I'm done with what I plan to show you. And if you have questions, please ask. If you have comments, if you have ideas of what could be very interesting to add or to have as a capacity, as a property, we are very happy to get this information. Thank you very much.
Thank you, Antoine. Thanks for a great demo. It's really interesting to see how all the tools link with one another. That was a really, really good presentation. So I have a question from Mark, which says, fantastic presentation. How sensitive is the HIA ellipse to the value used to constrain the growth of the ellipse? That's quite a technical question.
Yeah, it's a technical question. So really, the constraint is really soft, actually. So we really had to opt to use this one, not to have the ellipse growing too much at the beginning and having too large ellipses. So we have to constrain. But actually, depending on the optimization, maybe we could get rid of this constraint. It's really, let's say, a technical trick to converge more efficiently to something that makes sense. But I think the concept could be absolutely possible to apply without this trick, and really optimizing for MCC only instead of MCC and this little constraint. So it's really, let's say, a technical trick that do not affect either the robustness of the model, the predictivity of the model, and the classification ability.
And I have a quick question about the data that you're using to create the model from. So you've got data sets of about 1,000 compounds. Did you go to the primary literature to get those out, or did you get them from Campbell or something like that, or were they sort of published, curated data sets?
So for this kind of model, so for gastrointestinal absorption, PBB permeation, and the classification model, we go to the publication, and we curated them ourselves. So it's really the tedious part. It took quite a large effort to cleanse, because there are mistakes, but also to withdraw molecules where there are some signal of not being, for instance, passively absorbed, but being a transporter, and so on and so forth. Yeah. So it's really, we try to be at the root of the data more than using something that is already processed.
That's very interesting. Yes, you have a comment from Nina, who's in South Africa, who says, "Thank you very much. That was very interesting. Good comment." And I think we all agree.
Thank you. Thank you very much.
Oh, another one. This is also from Nina. If we use our own discovery molecules in this tool, will other people be able to see them, or are they kept confidential from other users?
So technically, we do not share, of course, the compound, and we do not look at them. But technically, they stay on a server that we administrate. Normally, it's perfectly secure, but zero risk doesn't exist, right? So if we get hacked, we cannot guarantee the molecule to be accessible. But yeah, so for instance, companies that have IP problems are very much welcome to contact us, and we have many possibilities to implement a dedicated server in their industry or having other methodologies. So we do that. We have also a lot of possibility of contracts. But let's say for these web-based tools, the classical web-based tools, we receive money to give these totally free to the entire community. So this means that it's public in the sense that everybody can access, but nobody has access to the data themselves, except we get hacked. Okay. So that's why there are a lot of disclaimers, legal disclaimers telling no, there is no warranty about security and confidentiality, but actually nobody is looking at the molecules.
There's a question here from David Matthews, which says, great presentation. How are possible tautomers dealt with in the calculations?
Sorry?
How do you handle tautomers? So if you've got an imidazole, do you take the tautomer as drawn, or do you allow for the other tautomer?
So the molecule are neutralized and standardized, but tautomers, the process is calculating only for this tautomer. So it takes the molecule as it is entered by the user. So here, for instance, you can have the two forms, right? The OH or the O-, depending. So if you want to get the whole information on that, you have to draw yourself the two tautomers.
Okay. And I think that's the end of the questions. Last chances for a question. Oh. No, that was a text. Okay. So that was fantastic. Well done, guys. I really enjoyed that.
Thank you very
much. So I think I'll have to find a way of setting up a poll, and we will ask people if there's anything specific that they want to hear about as well, because you clearly got so many tools here. Yeah,
for medicinal chemists, maybe docking is not the most interesting. We have, I think maybe the bioisoster stuff is something that can be also very useful for medicinal chemists. So if people are more attracted by this, we can adapt.
Yeah. Also, they are technically also we could make two tools actually in one webinar.
Yeah. Whereas the docking is pretty long, so the docking will not be so live, so we have to pre-calculate some stuff.
Okay, right. I'm going to turn the recording off now. So thanks everybody for listening, and come back and hear the second presentation in September. Okay, there'll be plenty more.
Okay, great. Have a nice summer. See you soon.
Bye, everyone.
Bye-bye.